Hello everyone, this will just be a little explanation of the prior worksheet covering stoichiometry and thermochemistry. Here we're looking at the combustion of ethanol in the presence of gaseous molecular oxygen to form carbon dioxide and water, as well as some residual heat energy that will be calculated later. Some of the information we're given is the heats of formation for each of our reactant and product species in their specific physical states, and also some molar mass of the elements that we can use to calculate the molar mass of necessary reagents. Of the questions we're going to be looking at, we're just going to need to balance our combustion reaction first, no matter what. Then we'll calculate the heat of reaction or the enthalpy of this entire reaction every time it occurs at least 1 mole of it. Then we'll calculate from 5 grams of ethanol combusted in this particular reaction. We'll determine the amount of moles of each reactant that would be consumed and the theoretical amount of moles of each product that would be produced from 5 grams of ethanol. And then after that, we will just calculate the kilojoules of energy released upon fully combusting those 5 grams of ethanol. Well, the balancing part's simple. It's going to be 1 unit of ethanol for every 3 O2s, yielding 2 CO2s and 3 molecules of water for each time this reaction occurs once. That was just from looking at ethanol, putting a 2 in front of CO2 to balance out carbon, putting a 3 in front of H2O to balance out the hydrogen, and then to balance out oxygen, we go back to O2 on the reactant side and put in a 3. Now, the reason why balancing the chemical reaction is important is because we use that for just about everything going further in most techniques with chemistry. For example, now that we have what is the balanced chemical equation relating each of our chemical species together in ratios, now let's see when they're all together, what's the enthalpy of reaction for that balanced chemical reaction? Well, that's just going to be the heats or the enthalpies of the products minus the reactants, with each chemical species multiplied by their stoichiometric coefficients. In this case, the heat of reaction or the enthalpy of reaction will just be 2 times the enthalpy of CO2 in the gas state plus 3 times the heat of formation of water. And then we'll sum all of that together. Separately, we will take the reactant side, which is going to be 1 times the heat of formation of ethanol in the liquid state, plus 3 times the heat of formation of molecular oxygen in the gas state. And then, once we sum all of those together, we'll take the difference of the product side from the reactant side. So in total, what we have is 2 times negative 393.5 kilojoules per mole, plus 3 times negative 285.8 kilojoules per mole, which that would end up being negative 1,644.4 kilojoules per mole. Then we have negative 277.6 kilojoules per mole, plus 3 times 0 kilojoules per mole, and that all adds up to negative 277.6, which, if we're subtracting a negative, that just becomes positive 277.6. Therefore, the heats from the product side minus the heats of the reactant side ends up becoming negative 1644.4 plus 277.6, or negative 1,366.8 kilojoules per mole, or more specifically per mole of reaction. Every time a mole amount of this reaction occurs, it's going to release negative 1,366.8 kilojoules of energy. Now, just some other relevant information that's usually important when we do different properties and parameters in chemistry. We should be able to calculate the mole amounts of reactants and products after we've balanced a chemical equation. We're told that we're combusting 5 grams of ethanol. Well, what's more important is to get into mole amounts, since we're going to be using that amount to go between different chemical species. From the atomic masses of the individual elements, the molar mass of ethanol is going to be 46.068 grams per mole. Since we're starting with a known amount in grams of ethanol, we're just going to multiply that amount by the reciprocal of its molar mass. So 5 grams of ethanol times 1 mole per 46.068 grams of ethanol. The gram amounts will cancel, and we're just left with moles of ethanol being 0.1085 moles. Now, what's nice is we're just asked to solve for mole amounts of each of these other chemical species. Therefore, all we really need is the mole amount of one, and then we can quickly get to the mole amount of the rest. For example, for the other reactant, for this balanced chemical equation, in order to fully react 0.1085 moles of ethanol, we're going to need to find how many moles of O2 would be necessary. And to find that, let's just take our 0.1085 moles of ethanol and multiply it by our comparison ratio, which is the stoichiometry coefficients of the species that we're just working with and the chemical species we're trying to get to. In other words, if we're trying to solve for moles of O2, let's have moles of O2 over moles of ethanol. And according to our balanced chemical equation, for every 3 moles of O2 that gets reacted, that involves also reacting 1 mole of C2H5OH. So 0.1085 moles of ethanol times 3 moles of O2 over 1 mole of ethanol just gives us 0.3255 moles of molecular oxygen. Or, in order to fully react 5 grams of ethanol, that's going to involve reacting 0.1085 moles of ethanol and 0.3255 moles of O2. Similar story, we can use this to predict the theoretical amounts or the maximum amount of each product that we can get to. One key here is that no matter what, if you're trying to go from moles of one type of thing to moles of a totally different type of thing, you need to use your stoichiometry from your balanced chemical equation. So if we want to go from moles of ethanol to the maximum moles of CO2 that might get produced, let's look at our balanced chemical equation, which says for every 2 moles of CO2 that got formed, it needed 1 mole of C2H5OH. So 0.1085 moles of ethanol times 2 moles of carbon dioxide over 1 mole of ethanol gives us 0.2170 moles of carbon dioxide. Similarly, when it comes to water, our balanced chemical equation says that every 3 moles of water that are produced is due to 1 mole of ethanol that was consumed. So 0.1085 moles of ethanol times 3 moles of water over 1 mole of ethanol gives us 0.3255 moles of water. Or from combusting 5 grams of ethanol, we can theoretically produce 0.2170 moles of carbon dioxide and 0.3255 moles of water. The last one is if we combust that 5 grams of ethanol in this specific chemical equation, what's the amount of energy that can be released afterwards? Well, we're going to need to just convert to moles or to kilojoules of energy from this reaction. Our long equation would just be that original 5 grams of ethanol times 1 mole of ethanol over 46.068 grams of ethanol. That's times 1 mole of reaction over 1 mole of ethanol times negative 1366.8 kilojoules per 1 mole of reaction. The reason we did that is because in order to go from one thing to another thing, for example, to go from grams of ethanol to eventually energy per reaction, or to energy, we're going to need our gram amounts of ethanol in moles first. That's why we'll multiply it by the reciprocal of its molar mass, which we already did that earlier, which is 0.1085 moles of ethanol. Now then, in order to go from moles of one thing to moles of another thing, we need the comparison ratio based off of our chemical reaction. For this, we just care about how many moles of ethanol are consumed for every 1 mole of reaction. Well, according to our balanced chemical equation, only 1 mole of C2H5OH will be used per 1 mole of reaction that occurs. So that's why we have our fraction of 1 mole of reaction over 1 mole of ethanol. And if we stop there, this just tells us how many moles of reaction will occur upon combusting 5 grams of ethanol. Because in part 2, we already calculated how much energy gets released per every mole of reaction, we can now add that to our calculation. So we either have 5 grams of ethanol divided by 46.068 grams times 1 mole of reaction over 1 mole of ethanol times the enthalpy of reaction, or negative 1366.8 kilojoules per 1 mole of reaction. And if we did that, we would get negative 148.3 kilojoules. Also, something that we can note is, since we're already calculated the mole amount of ethanol from 5 grams of ethanol in part 3, we can actually just skip the first half of that long equation and just replace it with 0.1085 moles of ethanol, and then just continue forward by multiplying by 1 mole of reaction per 1 mole of ethanol times the enthalpy. We could do the same thing if we use the mole amounts of any other chemical species in our reaction. For example, let's say instead of 0.1085 moles of ethanol, we instead used 0.3255 moles of O2. Well, while you wouldn't have to do this additional step, this is just to explain why we had 1 mole of reaction over 1 mole of ethanol. We already know that for 5 grams of ethanol to be reacted, we would need 0.3255 moles of O2. So hypothetically, if we use that mole amount to calculate the total amount of energy, we would instead multiply that mole amount by 1 mole of reaction per 3 moles of O2, because 3 is the stoichiometric coefficient in front of O2. And then we would still times it by negative 1366.8 kilojoules per 1 mole of reaction, and that still gets us negative 148.3 kilojoules. Main core of this lesson is primarily just understanding balancing the chemical reaction first, and then understanding how to apply the stoichiometry, those coefficients, for calculating the enthalpy of reaction, for calculating mole amounts of each reactant and product if we at least have some starting gram amount of one of them, and then finally combining all 3 parts, information from each part. For part 4, upon combusting that 5 grams of ethanol, what's the amount of energy that can be related? And what seems to be the trick that some have been having trouble with is understanding that comparison ratio, which is simply moles of whatever you're trying to end with over moles of whatever you just started with. And that's taking the stoichiometric coefficients from the balanced chemical equation as a ratio. In any case, that will be this little assistant review for our completed worksheet. And peace.